Alright, we're in section 2.3.2, estimating area with rectangles, and this is probably the most challenging section in chapter 2. So I'm going to try to break this down and make this a little bit more meaningful to you, and hopefully you guys can bring your questions to class. This will go at the bottom of 2.3.2, estimating area with rectangles. And really what we're going to do today is we're going to connect area under the curve to sigma notation. And we ended up doing a lot of the discovery in class, but I'll illustrate it graphically and then I'll try to kind of guide you through the process. So right below here, it's going to help if we sketch in an X and a Y axis here, just the first quadrant, and we'll go ahead and sketch in a curve, and we'll look at it on a given domain, and this is just to illustrate a concept. We don't need to necessarily make this super specific. And let's say we're dividing this into 4 different sections, so 1, 2, 3, and 4. Okay. Now, and actually, we're going to deal with left endpoint. So we're going to talk about left endpoint rectangles first, and then we'll talk about right. So this is called a left endpoint rectangle. And we're going to use these to help us approximate the area of a certain curve. So let's call our function here, f of x, and we're going to be using the left most point on this. So if we divided up our interval evenly, our first rectangle would be here, our second would be right around here, our third rectangle here, and this is just an approximation. I mean, if we were to do this by hand, it would be a lot more accurate if we were using our graphing calculator. So we're just to illustrate the concept, and our fourth here. So if we look at this area under the curve, we have 4 rectangles, and we've divided them equally. All their widths will be the same, and we're looking at the area underneath the curve, so the area of each of these rectangles. Now this is an underestimate of the area, at least of this curve, because we still see some gaps in here, so it's going to be a little bit lower. Now left endpoint rectangles, we'll write them in summation notation, and actually we should add one other thing. We should add the subscript. So we're going to call this x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. This is going to help us connect it to sigma. So if we wrote this, sigma notation, it would look something like this. Sigma of k equals 0, and we're going to say n minus 1. We'll revisit that in a sec. Now to find the area of a rectangle, it's base times height. So our height we're going to express as f of x of k, and our base is going to be called delta x. So we'll go ahead and divide both of these up. So if we looked at it this way, this is my height, and we can think of the height as my y value, and then delta x is just my base, and the base will be a fixed number because all the widths of the rectangles are equal. So if we look back up at our drawing, I could label this here as delta x, and this is delta x also. It's my change in width. That will be the same for each one. Now my height, it's going to be changing, and this is where it starts getting a little complicated this is going to be variable, so it will change, and we'll talk about how that will change in a second. Now k equals 0, that's where we're starting with our first term, which is here, x of 0, and n minus 1 would be my x of 4, but we're subtracting when we end at x of 3, which is here, and that should make sense because these are the 1, 2, 3, 4 points we're looking at. Okay? You will notice that this point over here, x of 4, never gets used because we're using the left-hand side of the rectangle. Now, we're going to look at right endpoint rectangles, and hopefully this will help kind of contrast it. So if we do right endpoint, I drop in the line here. Draw on your curve again. Okay. Now, drop this guy in. Drop this last one in. That is my air conditioner. Okay, so nice relaxing sound. We're going to divide this into 4 different quadrants again, so we'll go halfway. Now this time we're going to deal with the right. So if we're looking at right endpoint rectangles, now we're going to start with our rightmost point, which is here, another value here, 3, and then our last one, 4. Now again, these are going to be equally spaced. I know it might not look like that in my drawing. But if you look at these, this is going to be an overestimate of the area. You can see it's going to be a little bit too much, which is fine. Our x sub 0 and our x sub 1 all stay the same, so let's go ahead and label these. X sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Now these are called right endpoint rectangles. Alright, right endpoint rectangles. And here's our sigma, and there's only one difference here. So if we write our sigma in, we'll have k equals 1. Now we're going to start at our subscript 1, go to n, and then f of x of k times delta x. Again, your height and your base times height. So that's the same. Now the only difference is in this. N and k equals 1. So now instead of starting on the left side with x sub 0, since we start our rectangles over on the right side, we're using these points, we'll begin at x sub 1. This time we do not use x sub 0. The last time we used x sub 0, x sub 1, x sub 2, and 3. Now we're using the right. Now this looks like an overestimate, and I don't want you to generalize this. Some of you are going to say, oh, right-handed rectangles will always be an overestimate, left hand will be under. That's not true. What if we had a curve that... So if we had a curve that looks something like this, you don't need to draw it in, and it's decreasing, then all of a sudden, left-hand rectangles are an overestimate. So don't generalize and always think that left and right are always under over. It matters the shape of the curve. Alright, so now we're going to move on to the process, and this is what I think you guys were actually having a hard time with. So if we create a new slide, and you can put this next to it, we're going to talk about the actual process of the connecting this all to summation. So process, let's say from sigma to get the area under the curve. So you know how to basically write it now. Now we need to really figure out what this f of x of k is. So the process looks like this, and I think an example will illustrate this. So this looks like actually 78. So let's flash back to problem 278. So say we have problem 278, and I think 78 looked like this. You had f of x equals x squared, and you were on the domain 1 to 3, and it wanted you to divide it into 4 intervals that are equal. So that was the information it gave you. Now, our final form, so if we're looking at our final form, or where we're trying to end, needs to look like this. That's what we just did. You have a sigma. We're going to have k equals, oh yeah, and this, excuse me, is for left endpoint. This is for left endpoint. Okay, so let's say k equals 0, and we have 4 intervals. We're starting at 0. We're actually only going to go to 3, and we'll explore this in a second. It's going to be f of x of k times delta x. Again, the two things we need are our height, which is my y value, and we need our base, which is my change in x. So this is kind of our goal here. This is where we want to end up, but I want to talk about how we get there. So the basic process looks like this. The process will be, we need to go from k to x of k to f of x of k. And that will allow us to find our height, or our y value. Okay. Now, the base is going to be easy because with the base, we already know what our delta x is. It will stay the same. The question becomes, how do we find f of x of k from this information? Alright, so we're going to start, and I'm going to try to do this in steps. So let's look at step 1 first. Step 1 is going to be finding k. So, k. Now, we'll start like this. We're going to start with a number line. And we know we're going from the interval 1 to 3, and we know we're cutting it into 4 equal parts. So let's divide it up to 1.5, 2.5, and 3. Now the second part of this is our subscript. So x of 0, x of 1, x of 2, x of 3, and x of 4. We have each of these. Now, the question becomes, how do I create a relationship between these two things, k and x of k? Because that's what we're really trying to do right now. We're trying to figure out how do we get from k to x of k. So, if you look at it, it's a linear relationship. There's a constant rate of change, and there's going to be a y-intercept. So, we need to put it in y equals mx plus b form, which means we need two things, a slope and an intercept. Slope and an intercept. So our intercept is just our beginning number. It's 1. And you can see our rate of change is 0.5. So we are just increasing by 0.5 in each of these places. So if we were to write this in final form, it would be y equals 0.5x plus 1. The problem is we don't want to use x and y. We want to use k and x of k. So I will write this in here so you can see it. Our k will be in red, and then our x of k will do in black. It's here. So our final form here will actually be x of k equals 0.5k plus 1. Alright? Now, to talk about what this means, this is the x-coordinate, okay, at a particular, we'll call it the x value, or the x-coordinate at a particular location, okay? So that's our x of k. The problem is we need f of x of k. So if we've actually already done step 2, 1 and 2. Part 1 was finding k. Part 2 is finding x of k, which we just did. Now part 3 is this f of x of k. F of x of k is going to be our original function, which we have to go back to as f of x equals x squared. So if we have f of x of k, what we're doing is we're going back to that like f and g notation. It's going to be blank squared. Because our function is blank squared, we know what x of k is. We're going to drop it right in. It's this right here. We'll drop in 0.5k plus 1. Now what this tells me, it tells me the y value now at that point. So this is the y value, or what we needed earlier, it's the height. Okay, so now that I have f of x of k, I know it's equal to this expression, and my base, my change in base or my delta x, is 0.5, which we got from our difference up here, and that will always be the same. We can write our final sigma notation. So our final sigma will look like this. So sum of, now we're doing left, so we're going to start at k equals 0, at x of 0, and we're going to end at 3. And the reason we do that is because we are only using the left endpoint rectangles, so we don't use x of 4, just use those 3. So there's still 4 rectangles, it's just we're moving from left to right. And then my f of x of k is 0.5k plus 1 squared. That's my height. And my base is 0.5. It stays the same. So I have my height. And then I have my base. Again, my height's my y value. That's what took all this work. Flashback, it's really all about finding y. The base just stays the same. And the base will change based on how many intervals you have, but that's the easy one to figure out. The hardest part of this is area under the curve and really finding your process, finding height, and I'll write that in here. Okay. All right, I know this looks crazy. You're going to get better at it. It is a long process. It's a lot of layers. So hopefully this helps you see it a little bit better.